that's a very special occasion. That something is burning, and that it's a real privilege to be here to be able to participate in that. So actually, I don't have anything to tell you about quantum gravity, and so my talk would be more about. Well, I mean, there will be a couple of things there, but so I wanted to give some general overview, let's say, about quantum simulations, especially with cold atoms. And as you see, what I'm doing sometimes is just thinking loud about some ideas that I mean, probably most of you know, but I mean, you haven't thought very deeply about them, and so I wanted to revive them. And also to use experience of quantum simulations that I mean, have experience in some other fields, like in condensed matter physics or atomic physics or even in high energy physics, to see how I mean, maybe they can translate into the quantum gravity in the lab. Okay, so let me start being very, very basic, and I think that everything will be basic in my talk, so there won't be anything sophisticated. And so these are many problems that appear very naturally in physics, or even in chemistry, ranging from chemistry or solid-state systems, high-energy physics, and now quantum gravity. And all of them have in common that now you can use a language to describe them in terms of qubits. You can put the qubits and write everything, even if they are electrons or they're, I mean, high-energy physics particles in terms of qubits, write something like a Hamiltonian. And then we can try to solve problems with that, make predictions about what will happen with those systems. And we always face the same fact with all of them, that whatever we do with them, and we have many of these qubits representing our systems, then the resources that we have to use grow exponentially with the size of your system. So you write just the wave function in terms of a computational basis in this qubit system, then we'll have an exponential number of coefficients with the size of your system. And so this means that if we want to solve these problems with classical computers, then we'll have to pay a double price. So first of all, we will have to pay an exponential price in memory, because we'll have to store all these complex coefficients if we want to make any prediction. And at the same time, there will be an exponential overhead also in time, because if we want to compute each of them, and there are 2 to the n, then the time will be proportional to this 2 to the power n. So there's a double exponential, in a sense, that we are faced when we try to describe these quantum many-body systems in terms of I mean, classical computers. And in fact, one can think of what happens if I make a trade-off. So for example, imagine that now I don't have an exponential memory, but I want just a memory that grows linearly with a number of qubits. Then can I now maybe takes a bit longer with a classical computer to simulate the system? And actually, it's not a bit longer. It takes much longer. So probably it will scale like 2 to the n to some power that depends on the depth of your circuit. And so typically, the depth of the circuit is of the order of n, because you want to do, I mean, things with each of the qubits. Then it will be 2 to the n to the power n. So just trading space with time then actually gives a super exponential dependence of the computation. So this is why, I mean, it's the most natural framework, or the most natural place where to use a quantum computer is in quantum simulation, because you right away, as you know very well, we can use n qubits in order to store n qubits. So we have this exponential gain in space right away. And therefore, then, I mean, it's as I mentioned, very natural. So in fact, it turns out that there is even a bigger gain in some problems in quantum simulation. This was first realized by Seth, actually, that in 1996 he realized that actually, if you want to describe the dynamics of a many-body system in terms of these many-body qubits, and you have something like 2-body, 3-body, or 4-body interactions, like few-body interactions, then you can do it very efficiently. So it's not only that you will have to use a polynomial number of qubits, or a linear number of qubits with a system size, but also that the time that it will require in order to do it will be polynomial in n. In fact, I mean, later on, some people improved the algorithms, and now this is, I think, the best algorithm, that if you have short-range interactions in the system that you want to simulate with a quantum computer, then the computational time that you have to use will be linear in the size of the number of qubits that you have, and linear also in the time that you want to simulate, and will decrease like log of 1 divided by the epsilon, where epsilon is the error that you will have in the many-body wave function that you have. And as I mentioned before, this should be compared not only with exponential time that it takes with a classical computer, but the super exponential because we're using less memory here. That's why it's very natural to use, again, a quantum computer to solve quantum many-body problems.
Bosons?
Huh?
This for bosons?
This for bosons, but fermions it would be maybe a factor of n. But still it's polynomial, so it's an exponential. Yeah?
In what form do you get the result? Does this mean that the quantum state of your simulation approximates?
Right. Exactly. If you want to simulate for a time t with an error epsilon, that's the time that will take with in your quantum computer. I mean, the number of gates that you will have to do with your quantum computer, basically. Yes, it still is in quantum form. So, I mean, at the end, then probably you want to measure and predict some expectation value of an observable, so you'll have to repeat many times your experiment and to compute the mean value of your variable. But we know that this decreases like 1 divided square root of n, where n is the number of measurements, so there will be no exponential overhead. So, yep.
I didn't understand your greater than exponential. So BQP is contained in p-space, and I thought everything in p-space is exponential.
So I don't know. So what it means here is
your classical estimate. You said it was 2 to the n to the n.
Yeah, right, because the depth of your circuit will be of the order of n. So this is like 2 to the n squared. Right? 2 to the n to the power n is like 2 to the n squared. So it's 2 to poly n. And what I'm saying is that there exists, we don't know a classical algorithm that you use only polynomial memory. So you use only like n bits.
Yeah, but I thought BQP is contained in p-space.
Yes?
So that means that everything in p-space is exponential.
Even in computer science, polynomial in the end.
Oh, I see.
Right. So this is 2 to poly n. Okay. Anyway, so that's not the main message of my talk anyway. So now another thing that you want to do with quantum simulation sometimes is to look at thermal equilibrium. So to find what is the ground state of your many-body system. And actually we know that that's harder for a quantum computer. So because a QMA hard problem. And so the time that it will require will be 2 to the power n. Basically, there are algorithms, quantum algorithms, that achieve this task with 2 to the power n. And one would think at first sight that this is not as good as, if you compare with a classical computer. But again, we should compare it maybe with the 2 to the poly n that would take with a classical computer. So even for ground states, there is an advantage, even though the classical computer already takes an exponential time. Anyway, so all what I said refers to a quantum computer and to a fault-tolerant quantum computer, and where the error scaling does not depend on the size of the system. There are some assumptions behind that, so that's probably a scientific and technological challenge. So the question is whether now, like the experiments that are going on nowadays, they can still solve all these problems and gain this and have these gain factors. And in fact, so in principle, one could use these NISQ quantum computers, small devices that are a little bit noisy, in order to still solve some of these problems. And so, for example, if one wants now to make a quantum simulation of this quantum many-body system, and it's probably that in the next years it will be possible to use of the order of 100 qubits and make of the order of 1,000 gates, and that's the limit at which we could, just solve these problems with these first devices, which already is a lot. And I guess that's one of the reasons why we are here, because we probably can use these small quantum computers to solve some of the problems that I mentioned before. For the ground states, then, so probably, the best thing is not in practice to use the quantum algorithms that exist to solve these problems, but to use some more heuristic methods like adiabatic quantum computation or variational methods. And that's a lot of things that will be going on in the next years, just in this direction. However, here I want to talk about something different. Okay, so that's the setup. We know that there are quantum computers fault tolerant. If we had one, it would be wonderful for quantum simulation. We don't have one, and we will not have one for many years probably. Still, these first devices can, help us to the extent of what I mentioned here. But there is another possibility that is going on, and there are many experiments going on, and you have heard some of them in this workshop. And that's about analog quantum simulation. And in analog quantum simulation, the idea is not to have a quantum computer based on quantum gates with a discrete dynamics that will, just solve some algorithm, but is rather to imitate the system. So to have another system that we can control very well, to tune some of the parameters in this other system in such a way that more or less they describe the system that you want to solve. So one example is made by cold atoms in optical lattices. That's the one that I will concentrate on, in which the atoms can move in the lattice, and then you can control so how fast they move, what is the energy that they have, and certain properties, and in this way simulate other problems that are difficult to solve, and like in condensed matter physics, or as I will talk about high energy physics or quantum chemistry. Another that you heard this morning was cold trap ions, in the same way that you can tune the interactions using some external laser in such a way that the Hamiltonian that describes your system then emulates the Hamiltonian that you want to solve. And I mean, there are many other quantum simulations. We heard this morning also about superconducting qubits, quantum dots, photons, etc., etc. But here, what we gain right away is what I told you before, that we are using qubits in order to describe qubits. So we have this gain in space. So we don't need an exponential memory, but just using the system itself with n particles, we can simulate the problem with n particles and quantum particles. So what are these advantages and disadvantages between analog quantum simulation and this more quantum computation? Well, first is control. So typically in physics and in chemistry, many of the problems that we have, they have many symmetries. So for example, they are homogeneous, they are translationally invariant. So this means that the Hamiltonians that you would like to simulate, you don't have to address each of your individual qubits independently, but maybe you have a global parameter. And with this global parameter, you can tune it. And that's much easier to do experimentally than just tune many, many parameters independently. So one advantage is that you don't need such a degree of control. But maybe the most important advantage, and I mean, that's controversial, but I think that, I mean, there's, so I'll explain some reason behind, is the how errors may accumulate in analog quantum simulation as compared to a quantum computation. And the idea is that, you see, imagine that I have a Hamiltonian that I want to simulate. This is this Hamiltonian here, which, for example, I have one of these lattices, and you have nearest neighbor interactions or some region of interactions. In any of these experiments, since the Hamiltonian is not coming from first principles, there would be some error. So it means that your Hamiltonian in practice will have some other term, maybe some epsilon, some small parameter. But actually, the number of terms that you will have in your errors will typically scale also with the size of your system. So for each interaction that you have, since it will not be perfect, there will be some error. So it means in practice that even if this epsilon is small, there are n terms or many terms there. And so this will explode. So this means that if you have a sufficiently large system, then this term here will be much larger than 1. So you cannot do perturbation theory. And therefore, it seems that this is not going to work. And that's, I mean, this occurs in all experiments. So the errors are extensive in all these systems. And so you want to use this system for quantum computation, then what will happen is that in the middle of the quantum computation with probability basically 1, the qubits will flip and you will get something that has absolutely nothing to do with the result that you want to say in order to solve a problem in factoring a number or something like that. However, the question that we're asking in quantum simulation is not to get the many-body wave function. It's not that we want to have an overlap with a many-body wave function, which is of the order of 1, but we are looking at some physical quantities, and these physical quantities are intensive, meaning that what we look at as expectation values operators per particle divided by n. And the fact that we have something that is divided by n, somehow, in some cases, it cancels the fact that you have an n term there. And so it means that even in the presence of error, you can get let's say, these quantities with, you have this epsilon is, let's say, 10%, then you can get the outcomes of your measurements and the predictions that you have in intensive particles of the order with an error of 10% as well. And of course, this is not rigorous, but that's something that happens in practice, and this happens very often. And whenever you talk to computer scientists about something like that, that's not the framework in which they formulate the problem. So they talk about complexity, so they want to solve problems in which the parameters grow with the size of your system, whereas in many of these problems, the number of parameters is constant independent of the system size. You want to know what happens in the thermodynamic limit. And I talked to many computer scientists about that, and one way of, then they basically say, well, this cannot be right. There's something that is wrong. But the best way is just to show an experiment. So as you probably know, in 2002, there was an experiment with cold atoms in optical lattices, which was mentioned here, where they realized the experiment of multi-insulator to a superfluid transition. So basically, they took the Bose-Hubbard model that this morning was mentioned, and they simulated with cold atoms in optical lattices. And you can go to the, read the paper experiment, and you will see that the error that they had in that experiment was very big. So this epsilon that was here, so they wanted to simulate some Hamiltonian, they had errors, and this error was of the order of 20%. And they make some measurements, and the question is that they wanted to see that in the experiment they saw some prediction. This turns out that the Hubbard model, you can solve with some other methods, with Monte Carlo, and then you can make predictions, so you can benchmark your system with that model. And what they were able to see is that the predictions were very accurate with respect to what they have, even though they had a very big error. And you don't have to know physics to see that. What they saw is that if you have some number of parameters, what they observe is something like that. They change the number of parameters, they observe something like that, and then they change again, they observe something like that. So there is a phase transition here very clearly. So something prominent happened, and it happened at the right place. So actually this, this at the end is some measure that is kind of interference experiment, and then they see that there is some visibility here, there is no visibility, there is a visibility. But what I'm saying is that even though, they had of the order of 100,000 atoms, so this error here is, let's say you can say it's huge, enormous, but still you're able to observe and to make the measurements on these intensive quantities and answer the physical question. So that's, I think, that one of the messages that I want to make, that for these analog quantum simulators, if you're looking at things like ground states and things like that, even if the errors would be crazy for a quantum computation, still you may be able to answer some physical questions, like in experiments that are noisy. And that's why it's interesting, even though, of course, if one compares now with classical computation, I think that nobody's building anymore these analog classical computers. But since we don't have digital quantum computers, then maybe still with analog quantum simulation, we can resolve some of the problems that are interesting from the physical point of view. Okay, that's also related to what Misha was talking and giving his talks. So what could be the goals then in general of analog quantum simulation? So we have heard here many of these goals. So one goal could be to solve a specific problem. So one has Hubbard model for fermions, and you would like to know what is the phase diagram. And this could be one. Another one is to provide some understanding. So maybe by doing these experiments and then measuring things in situ, then you can learn physical phenomena that are happening there. And but I think that there is even a more interesting purpose of all these algorithms or all these quantum simulation experiments, and actually it's to benchmark theory. So if you think about that, we don't have theories to describe classical theories, numerical for classical computers methods for solving many-body systems. And so, of course, we have now tensor networks, we have machine learning methods, neural networks, and things like that. But all this cannot be benchmarked. So you can try one, and then because you think that you had the feeling that this will work better, then you try another one, but there is no way of benchmarking. If we don't do it one with each other, but that's not an absolute measurement. However, if we had these analog quantum simulators, we'll have a way of benchmarking this method and learn from them, and I think that that's probably the most important application of these quantum simulations. And so this is one example that, that occurs in the group of Immanuel Bloch and Christine Ross. So they did this experiment on with cold atoms in optical lattices about so what happens if you have a disordered potential and you have atoms in 2 dimensions. And so before, people discuss what will be the dynamics of such a system. You let atoms move when there is some disordered potential. And actually, this is something that, at least before the experiment, was very hard to describe, so with numerical methods. They did the experiment, they observed some localization, and then after that, then people realized that already with Gutzwiller projection, with some very simple methods, you could describe the system. So what we learned is that actually there is a method that can describe this kind of experiments very well, that it was not clear from the beginning that this would be the case. Okay, so I'm going to talk a little bit now about cold atoms and optical lattices, and then probably you know it already, but the idea is that you have some external laser fields that have some interference pattern. They create some kind of periodic potential for the atoms, and the atoms are holding these potentials, and they can tunnel from one potential well to the next one. And if you just take, kind of basic principles and and take this in the Hamiltonian describing the system and project it in the low energy sector, then you will have a Hamiltonian that would look like that. So, I mean, atoms can tunnel, can move in the lattice, and then when they meet at some lattice site, they interact with each other, so there is some energy related to that. And it turns out that this automatically, you can see, that can simulate the motion of electrons, for example, in material, which also they can move and can interact with each other if they have some screen interactions. And so that's why atoms in optical lattices, without no effort, basically, they simulate Hubbard models of this kind. And now you can play with geometry. So, for example, I mean, you can have a square lattice if you just take the lasers, just having some spatial geometry, but you can change the geometry. You can have different kinds of lattices. You can use fermions, you can use spins, you can use bosons. You can have 1 dimension, 2 dimensions, 3 dimensions. So it's a very flexible system if you want to investigate I mean, the physics of Hubbard models. And that's why, and actually, one of the main restrictions that the system has, and if you're thinking about quantum gravity, or at least some of the models that we mentioned here, is that here the interactions by themselves are very local. So if you take these experiments, most of them, the interactions only occurs if 2 atoms meet at the same potential. If you can have, like Misha mentioned in his talk, that you can excite the atoms to certain Rydberg levels, then they behave like dipoles, and then they have some long-range interaction, but this long-range interaction decays very fast, decays like 1 over R6, or 1 over R cubed, which is a very short interaction as well. But you could think of what Monica was telling us, to use cavities in order to have like a longer range interactions, and at the end of my talk, I'll give you some idea of or some of the methods in which you could do that. Okay, this has, as I mentioned, applications in condensed matter physics, but actually it turns out that it has also can be used also to simulate high energy physics, lattice gauge theories, and I'll talk now about that. But it turns out that also quantum chemistry and the difficulty goes in this direction. So, I mean, to do the experiments to simulate condensed matter physics problems is difficult. High energy is much more difficult, and quantum chemistry would be even more difficult, at least for some of the experiments. And of course, we hope that we will also have some applications in quantum gravity. Okay, so let me talk now about the simulation of high energy physics with cold atoms in optical lattices. There have been many people working during the last 5 to 10 years on that. And so in my case, I started with Yanis Pajos and then continued with Benny Resnick and RSOR. But there are some other groups in Barcelona, Bern, Innsbruck, in some other places also making some proposals for that. And so these are some of the basic ingredients if you want to simulate high energy physics models like lattice gauge theories in the system. So first you have, so typically in these high energy physics models, you have 2 kinds of particles, or they are like matter particles and gauge field particles. And so some of them are bosons and some of them are fermions. Also, these theories are relativistic. They are also gauge invariant, so it means that there are many symmetries. There are local symmetries in your models. And another thing that it's at least that people working with cold atoms, they would like to have a Hamiltonian formulation, because typically you work with the language of high energy physics and still have to translate it to the language of, let's say, atomic physics. But it turns out that all this is very straightforward with cold atoms in optical lattices. So the first thing is that you want to simulate matter and gauge fields, but you know that we have species of atoms that are bosonic and some species of atoms are fermionic, depending on the spin that they have. And so this means that you will have to put together bosons and fermions. The fact that they are relativistic doesn't mean that you will have to take your atoms and accelerate at relativistic speeds, because we know that for many fields that actually that a lattice does the job. So you have a lattice, if you want to have a particle moving on a lattice, then it will see some dispersion relation. And the dispersion relation has some linear parts. And in the linear part, I mean, the behavior is relativistic. So you go to the energies in which you see a linear dispersion relation, then you see that in the continuum limit, you will have the right properties that you want. The fact that this gauge invariant, all these symmetries, actually this happens also very naturally in the atoms. So the atoms have certain symmetries. So when the 2 atoms collide, then they conserve angular momentum. And so you have that the collisions occur locally at the different positions, then the angular momentum will be conserved at each point. And it turns out that you can translate this conservation law into the gauge symmetries. And the Hamiltonian formulation, we don't have to do any effort because we have the formulation from Lenny, and this gives already just the Hamiltonian. So basically, you want to simulate lattice gauge series with collaterals, what you have to do is basically a translation from what people have in the labs to this language, and that's relatively simple. So for example, I mean, in two spatial dimensions, so 2 + 1 dimensions, then we know that in a lattice, what you have to do is just to maybe some stagger fashion. So to put your degrees of freedom of matter, your fermionic degrees of freedom at the vertices, the bosonic degrees of freedom at the edges, and then the Hamiltonian will tell you that there will be some Hamiltonian corresponding to the matter. This will act only on the fermionic degrees of freedom. That will be, for example, mass terms. Then would be on Hamiltonian for the field. So we'll have an electric part which will act only on the on links, and the magnetic part that will act on plaquettes now of your bosonic system. And then some interaction, which means that when a fermion just hops from one place to another one, it interacts with the boson that is in between. And then you have to make sure that in this interaction, then you have this gauge symmetry, which will be dictated by some gauge group. So we'll have to have some certain property, and you have to just find a way of translating conservation that you have in atomic system into this symmetry, and that's relatively straightforward. So that's why, at least on paper, it's relatively easy just to translate, and I mean, to translate the physics of cold atoms to simulate this lattice gauge series. Actually,
how big is the Hilbert space on each link?
Well, you will see, it depends. So at the moment, it depends on what you put. So you can put like two internal states, bosons with two internal states, and therefore, then in principle, it could be infinite. But you could have an infinite number of atoms there, and so the information would be in the phase difference. This would be just like the phase operator that is conjugate to the electric field. Yes. You can do non-abelian series. So people have come out how to do that, and the idea is just to use in a clever way. It's like a Lego. No, you have a Lego, and then you have to give me SU3 whatever Young Mills, and then you can do that. So there are ways of doing, at least in theory, and in the experiments it's more difficult. And let me tell you why is it more difficult in experiments. So actually, it turns out that in 1 + 1 dimensions, that's relatively simple. So that's a way of doing that. So you'll have your stagger state. So you'll have to have like a super lattice. So this is like the optical lattice, which has even and odd size. So one would correspond, for the simplest case of a U1 theory, one would correspond to the particle, the other one correspond to the antiparticles. And then in between, you will have what I said before, two species of bosons, so bosons with two internal states. And now the difference of bosons, yellow bosons and blue bosons, will be your electric field. And then you have to make sure that whenever an atom hops from one side to the other side, it changes the spin, and it also changes the spin of one of these particles, transforms one of the yellow particles in one of the blue particles. And if you have that, then automatically you have the Schwinger model. And you can get more complicated models. And that's, basically the physics that these atoms already have in the optical lattice. So that's, I would say that it's not straightforward, because you have to put the two species together. You have to use superpotential and so on. But that's not that difficult. When it becomes more difficult is when you go to higher dimensions. And the reason is because then you have plaquette terms. So you have four-body interactions. And atoms, they have two-body interactions. So you have to make out of two-body interactions, four-body interactions. In the same way, for the SYK model, you need out of two-body interactions to get four-body interactions. And in principle, this is always possible, but you have to do perturbation theory. You have to, you go to second or fourth order perturbation theory, you can have four-body interactions. So Sui says no, but anyway, in the way of cold atoms, that's the way that people have proposed to do it. And then it's more difficult, because when you have to do perturbation theory, it means that the thing that you get at the end will be much smaller. And so it will be hard to go to a limit in which this interaction is sufficiently hard. And also, experimenters, they don't like to work in perturbation theory, because then already the numbers that they have to fight with the coherence. So if the time scales, see the coupling gets very small and the time scale is very long, then they probably will not work that well. However, there are some other, now you can come from quantum information and learn some other tricks in order to get around this problem of perturbation theory. There is another way of getting four-body interactions, just using ideas of quantum information, which is just take a particle here. So you would like to have a four-body Hamiltonian, or the evolution according to some four-body Hamiltonian, this four bosonic here, but you can put this an ancilla in the beginning and make the ancilla to interact first with the one, then with the other one, then with the other one, then with the other one. And this interaction, actually, you can see, I mean, you just do it like with qubits, and then you can see that the particle in the middle can non-perturbatively mediate the interaction between the four particles, and then you get a four-particle interaction. So in this way, so for example, you can think that you could have now your atoms in optical lattice. You will have an ancilla, and this ancilla will have to just stroboscopically just move around, interact with all of them, and in this way you could get the four-body interaction. That's one possible way, and this also may bring some ideas also for how to simulate some other four-body interactions with cold atoms that are required for some other models. Okay, anyway, so I wanted to just, this is a little bit aside, mention that, so actually it turns out that in lattice gauge theories, you have fermionic matter and gauge fields. It's possible to eliminate the fermions. So it's possible to do a unitary transformation that gets rid of all the fermions. And then you have a bosonic theory at the end. So I don't have time to explain it, but basically you give me a Hamiltonian. I can find a unitary transformation that is local, in which you get another Hamiltonian that is still local, but now there are no fermions anymore. There are only bosons. And this has applications because in any spatial dimension and with any lattice gauge theories. Actually, we found that there is a way of doing that in general. And so this means that actually fermions are, I mean, in principle, you could live without fermions at all in lattice gauge theories because you don't need to formulate anything. But also for quantum computing, it means that now you have a quantum computer with qubits, then you don't have to have string operators there. You can do it in fermions, but also for analog quantum simulation. So now you have superconducting qubits, or you have trap ions, which are bosons. There is no way of getting fermions. Then in principle, you could also do these analog quantum simulations because you have only bosonic degrees of freedom at the end. And so maybe this also is useful in quantum gravity, some of these tricks, even though there is different, because here it's very important that you have these gauge symmetries and they are local. And so you have something that is not local, it would be much, much harder to do something like that. And so finally, my last minute or so, I wanted to mention something that we recently did, which is to show how you can simulate quantum chemistry using cold atoms in optical lattices. And just let me go to the point, and also maybe can be exported some of these ideas to quantum gravity. The idea there is that you can work in the Born-Oppenheimer, where you fix the position of the nuclei. And given the position of the nuclei, what you would like to know is what is the motion of the electron. So what is the electronic state of your system? And then as a function of the position, just compute that. And this will give you, for example, some energy potential, some molecular potential. So the idea is that you should be able to have the Hamiltonian describing chemistry, so kinetic energy of the electrons, then the interaction with the nuclei, which are static here, have an infinite mass, and also the electron-electron interaction. And I mean, the first part is single particles, so that's not so difficult. You can have some potentials when you could have fermionic moving on the lattice. This would be moving is the kinetic energy. Then they are attracted by some external potential to some particular places. This would recreate the interaction with the nuclei. And the difficult part is the interaction between the electrons, because this has to be Coulomb, has to decrease like 1/r. But I mean, you can show is that actually you can simulate what nature does in practice. In nature, when you have two electrons, the way they interact, because they exchange bosons. So what you can do is you have to put a bosonic atom that mediates the interaction, and actually we figure out how this can be done. So this means also that you put fermions, or you have any system, and then you put another particle. This other particle can mediate long-range interactions, and that may be also useful for another way of getting long-range interactions as required in some of the models that have been discussed here. Okay, so to finish up, so the messages that I wanted to convey is, first of all, okay, quantum computers are very good for handling many-body problems. So actually, the most natural problem that a quantum computer can beat a classical computer is a quantum many-body system. So the quantum supremacy would be kind of obvious. It should be for solving these many-body problems. Then maybe we don't have a fault-oriented quantum computer. You can use NISQ, or you can use analog quantum simulators. And in analog quantum simulators, as I mentioned, I mean, one of the advantages is the control. You don't need a full control over everything. And also maybe the robustness that I mentioned in terms of we are interested in intensive quantities and not in extensive quantities. And so I mentioned that this has applications in different fields, hopefully also in quantum gravity. And so the goals maybe to solve problems, some particular problems that are hard to solve with classical computers, to learn phenomena, but I think that one of the most important ones would be to benchmark methods that can be used to describe these systems. So thank you for your attention.